Hello everyone, welcome to another episode of Solving Advent of Code in Rust and try to learn Rust, more or less. I'm Roberto and we have...
I am Luciano.
Thank you everyone for following along. If you never did Advent of Code, Advent of Code is a challenge that is published every year around the Christmas period. We are working toward the last year one. There are 24 challenges and you can find them on adventofcode.com. We are publishing all our code in a Git repository, this one. And we have a YouTube channel where we publish all the recording. You can find the link in the description of this Twitch channel. Last time we did exercise 17 part 1. That was a game of life in 3 dimensions. And now we have to do the next part. That, spoiler, is the game of life in 4 dimensions.
But before doing that, we should check a PR or what?
Yeah, right. Before that, we have Tommaso that sent us a PR for, I think, exercise 16 about some clever stuff that we were doing in a not so clever way. And yes, it's better to merge them also because they make the code faster.
So I'm gonna show that PR. By the way, thank you, Tommaso. I don't know if you are watching, but yeah, you are sending us a lot of PRs, so you are most welcome there.
Thank you. So yeah, basically we were doing a filter map with a strange logic to filter out the not correct, what were the tickets? Okay, it was the tickets exercise. So some tickets were not valid and we were filtering them out and converting the numbers in a vector of numbers, everything in one step with a filter map. But there was a strange if, line 95, that implied us to allow a specific clippy comment to avoid to have clippy complaining about this. Instead, doing a map and then a filter this time. Normally, we do map and filter, and then Tommaso tells us, do a filter map. This time, we did filter map, and Tommaso told us, do a map and a filter. So we can never get it right, basically. If we do something, please, guys, do the other way around. And
this was the bulk of it. The other one was also very interesting, this guy.
We tried, when we were doing this, to use the unstable feature that was like drop the elements that are matching or not matching this Boolean expression.
Was something drain, I think, was the name of the function.
Yeah, that was giving you back a set with all the drained elements and keeping and modified the original one. But in the end, we just wanted to modify the original one. So we missed the retain function that is doing exactly that. So modifying the set in place and based on a Boolean that we already had because we implemented it for our if, keeping only the stuff that we needed.
And that was it. Oh, and here as well, it's more idiomatic, I guess, rather than doing for loops. We use
we are keeping a collect to materialize the vector somehow, I think. Instead, that filter map is doing them on the fly.
Yeah, and here we were doing the product like manually in a for loop, while here there is an iterator method to do the product.
Yeah, because it's a vector of integers in the end, of some kind of integers. So there is the product one. I always forget that there is product sum and all kind of stuff on top of vectors.
Me too.
Yeah. Oops.
Okay, so I'm gonna merge this one. I think
also this one with this one, the test of exercise 716 become 22% faster,
which we can see here.
Yeah.
So thank you for the great solution, which is also faster. Right. So now I'm gonna pull, and we'll switch back to doing some code by looking at the next part of exercise 17, which was the one where we were doing essentially the game of life, but in a variation where the game of life is initially in 3D, and I think now we'll need to do it in 4D. So basically, let me do a super quick recap,
Go to the README probably is a good place to start from.
Roberto, correct me if I remember this one wrong, but basically I'm going to start from the input. So this is basically initial state of our game of life, where every hash is a cell that is currently alive, and every dot is essentially a dead cell. Now, the interesting variation here is that generally in the game of life, you change this grid, you kill some cells or you make them alive, depending on rules, and every iteration that the structure of the current table changes, because you will have new cells that will become alive, other cells will be dead, and this is always changing. Now, in this variation, you basically have to imagine as if this is a 2D plane, but every next iteration, this 2D plane, you can also grow top and bottom, so it kind of becomes 3D. And of course, at every iteration, it keeps growing more and more in all the three directions. So, and basically what we needed to do, we needed to start from this one as a plane, then start the second iteration, it becomes a cube, and then it keeps growing, and we needed to do 6 iterations, and then at the end count the number of active cells in the entire space.
Yeah. Also, and the space is infinite. Normally, some implementation of Game of Life in 2D, you have a board that is 10 by 10. And the border, you can go outside of the border. Here, the space is infinite. There is no limit to it. So, and we see that with 4 dimension is even easier for us because it's hard to think in 4 dimensions, I think.
So you have to imagine that you can go, like, even if this is line 0, you can go to line -1. So for instance, here you can have a new line eventually where some cells will become active. And you can do this in every direction. So the same on this side, and the same on this side, and the same on this side. So of course, the more we keep running, the more it kind of expands.
Or shrinks, depends.
Or shrinks as well. Yeah.
But not in a too predictable way. So we can't allocate a fixed size matrix to do this.
So our idea was to use a sparse, an hash set, which basically represents a sparse set of points. And these points in space are only the active ones. And basically our solution is, for part 1, what is it doing is just taking all these points here, and then it's calculating the next iteration by looking at the ones that are active, all their neighbors, and then considering all the rules only in these ones. And this is an optimization because we realized that only the current active cells or the neighbor of these cells are the ones that will potentially change state, either die or become alive. And therefore, we don't need to consider all the entire space, every single cell, but only the interesting ones. And we did all this logic here in next state, where we have these points to check. Initially, we start by taking all the neighbors of a given point, and we do that for every single point that is active, because we only store the points that are active. And then after that, we count the neighbors, and we decide if... we count the neighbors, and then if the current point is alive, we apply the rules based on whether the current point is alive and how many neighbors are there, and we decide whether it's true or false. So if this interesting point will become alive or die. And then when we collect, we get a new cube, which is our representation of the space. So it's going to be a new hash set of points that are active at this point. Make sense?
Yes. Why is underlying some stuff? Last time it was... I hope it's still running. You have some underlines.
Yeah, this underline is because I have Clippy, which is suggesting me to use this macro, which, if I remember correctly, works this way. So you can say this, I believe, and then remove everything else. So this is basically saying, because in our pattern matching we were returning true or false, this is kind of a shortcut saying if this expression matches this pattern, then it's true, otherwise it's false.
Okay, so
it's kind of a nice sugar.
Okay, syntactic sugar, but in the end, yeah, I like it. Just this macro is. Do you have to import it? No, it's already
no. I think
in
it's
the standard
a
library.
default one. Yeah.
Okay, cool.
I don't think it imported anything automatically. No.
Okay.
And then I think as soon as I saved, my IDE also formatted everything. So that's why we see other changes there.
Oh, fine. The linter strike again.
So that's it. As per part 2, I'm gonna double check the README just to be sure we understand what it says. But we already had a look. I'm not gonna hide it. We did a little spoiler this week. So basically what it's saying us is the pocket dimension contains an infinite 4-dimensional grid at every integer 4-dimensional coordinate. So now we have a new dimension, which is W. There exists a single cube, so a single point, I guess. We just call it point. Here is cube. We'll probably change the wording because we made it a little bit confusing. So here is called an hypercube, and this can be active or inactive. Okay. So now, since we have 4 dimensions, the neighbors are more, because before we had, 26 neighbors?
Yeah, 3 to the power of 3, 27, minus
the center point.
Yeah, the center point.
And now it's 80 because, of course, you are looking at 4 dimensions. So you have 3 at the power of 4 minus 1.
This is 81 minus 1.
Okay. And so that's the main difference, because we added a new dimension. We have to consider more neighbors. Like, I cannot imagine this for this space, but if you could imagine it, of course, you need to expand in an additional dimension. So the initial state is always the same. So we always look at the same input, with the difference that, again, you are only looking at one plane, and then you will keep growing in all the other directions. So the ask is the same, that you need to simulate a few cycles, and this is an example.
This is a very long example, because they are splitting all our hyperspace in slices to be able to write them in a README, and it's basically useless because you can't imagine them together.
So the question is, after 6 cycles, in this example, there are 148 active cells. And what we want to do is, starting from our input, how many cubes are left in the active state after 6 cycles? So it's exactly the same question. The only difference is that now we have to assume that there is this additional dimension. Okay, so I'm going to suggest that we do... Actually, there is a question here. Let me reply to that. Apologies if I don't look at the chat. Do a lot of noise there. Keep writing. I will eventually notice. So it's more of a comment from Tommaso. I think you can allocate before a static memory if you know how many iterations you will make.
We are doing 6 iterations, but I don't know how many. So we know because we have the solutions there. So, but I don't even know if the solution is 1696. But the step previous to it, they can be more, because it can be that between iteration 5 and 6 they shrink rules. I don't know, chaos rules. They're not chaos. Game of Life rules, so I have no idea. So I don't think you can predict very well how many points you have in your space or hyperspace just with the starting configuration. So and also, if you have a different start configuration, you grow with a different number of points. So I would like just to have an hash set and go. I don't think we can
also, I don't expect that pre-allocating everything especially for the 4D variation, will be faster because it will be a lot of points, right? And the more it grows, if it grows, the more points will be exponentially. So I don't know. I wouldn't feel like that's a scalable solution. Then, yeah, if we really know a specific configuration and we know it doesn't grow too much, maybe.
An objection to what I said is the next comment, but that can be true. You have a 6x6 grid, you make 6 iterations, so you can go only 8x8. Sorry, our input is. You can go 6 in this direction, 6 in this direction, 6 in this direction, and 6 in this direction. It becomes 6, 6, 12, 20. 20 by 20 by vertically, you become 13. But I think that 20 by 20 by 13 is more memory than our hash set. It's for sure more memory because our hash set is not ending full. For step 1, our hash set is ending in, can you see the test in part 1, Luciano?
Part 1 is 280.
Yeah, 280. Only 20 by 20 is 4,000. By 13, no, sorry, 20 by 20 is 400, sorry. But well, 400 by 13 is 40,000, more than 40,000. You can allocate a matrix of 40,000 booleans. Probably Rust is even a lot efficient in doing that. But probably having a hash set of integers, just 280 is more memory efficient, I think. Mm-hmm. We could try to implement the brute force matrix solution, but it's just probably less efficient from the memory point of view. Also because we are always cycling over a lot of points that can't become alive because they have 0 neighbors. Instead, with our implementation, we only take in account points that have the potential of becoming alive.
Mm-hmm. Or they are already alive and they might die.
They are already alive, so they have the potential to die. Or they are dead, but they have the potential to become alive.
Okay, so going back to part 2, now we have an interesting challenge, which is we defined a bunch of helpers and structures that are working on a 3D space, and now we need to do it in a 4D space. Mm-hmm. I know that in Rust there are ways to kind of generalize that, but I want to take a little bit of a dumb approach intentionally where I'm going to do a copy-paste and replicate everything in 4 dimension, have a working solution, and then when we get there, if we have still time, we can figure out how to maybe refactor to avoid code duplication.
Yes, normally also, for the guys that are seeing us for the first time, our approach is we go to a working solution, then we refine it until it's better.
Mm-hmm. Well, better for us. If you, after the episode, you still think that there is better, please send a PR or send us comments.
Yes.
The first thing that I want to do, by the way, because this is going to be confusing, I'm going to rename this guy Universe rather than Cube because, yeah, I think it's better. And actually, I'm going to rename this everything basically point 3D and Universe 3D because...
Have you done a refactor? Or?
I didn't. Apologies. Rename point 3D and this one rename.
No, for that one you did it because... okay, Universe 3D, okay.
And now, of course, I want to do the same for 4D. So we do point 4D, which is I32. I need to figure out this keyboard. And universe, I'm just going to copy this because I'm lazy. 4D and 4D. Now, let's see how much copy-paste do we need to do. Neighbors of point. This is definitely something we need to change as well in 4D. So let's rename this.
Question, for example, based on the type of the parameter, languages, other languages detect which function to use. Rust is able to do that, or is not the case? How it works?
Oh,
For
you
example,
mean
if you create another neighbor of points that takes a parameter that is not a point 3D but a point 4D, Rust can have the same name for the function but with different parameters, or is something that
I don't think so. I know you can do that, for instance, in Java, but let's try because it's an interesting question. So basically, let's say that we did
leave the old name, but instead of specifying
we
the
use
name
4D and return 4D.
Yeah, then
let's see. No
overloading of the functions.
Previous definition, yeah, you cannot overload based on arguments. I think you could use traits, like if you had a generic, I don't know, something like implement point, I guess, you could probably do that. Or there are other approaches like const generics that we could use here to have things with an arbitrary size. But we will probably discuss that later.
Yes, let's start with the stupid solution. Then we can use this. In the chat, we were talking about type parameters. That's probably what we were talking about. So call this function with this type.
Exactly. So here now we have 4 dimensions, and this is going to be 80, we said, right? And we need to add an additional loop, which is going to be for w in -1 equal 1. And basically here we need to add 0 and we need to add w, and we do w plus point.3.
Yes, and I think everything else is the same. No, that 26 up there becomes 80.
Oh, yes. Okay, that's why it was complaining.
In the return parameter, yeah, there.
Okay, now count active neighbors. Again, we'll need to make it 3D. This is a little bit annoying, but bear with us because I think it's going to be interesting to see if it works first and then generalize it. So this will be 4D. We get point 4D, universe 4D, and we want to get neighbors of point 4D, which is the one we just implemented, and point, what's the issue there? Point expected a reference, and we are giving it, did I change something there? Oh yeah, I removed that by mistake.
Okay, sorry. I missaid it.
Yeah, I didn't realize either. Okay, now we have next state. Again, I'm going to rename this 3D. Nope, no refactor, rename 3D. And we do a copy of all of this, and we do 4D. And I think this is the last one we need to change. 4D, universe 4D, and it returns another universe 4D. It takes this 4D. And now, what are we doing? For point, this is 4D. Okay, and all of that should be okay because now we get 4 dimensions. Now points to check.
Okay, then line 90, yeah, there.
And old cube, we should probably rename it to old universe.
Yeah. Refactor it to old universe.
Cool. And also here, I guess.
Yeah, in that case, it's still a cube, but well, okay, let's go for old universe.
Yeah, let's keep it consistent because I think it's going to be easier than to refactor. Also, I don't think here we need to pass a reference because it's already a reference, I think.
That was working
even here. No, I think Rust automatically the reference there, but Clippy complained saying you're doing stuff that is not needed. Okay, now we should have all the building blocks. I suppose, again, we can just copy all of that and here change it. And now we want to do a universe 4D new. Now we get the input, which
remove the underline.
And now we have an additional dimension, which is 0. And that should be enough for us to insert. And next state for D.
Also rename cube in line 117.
Good point.
Rename cube.
Okay, that's it. How much are we confident this is going to work?
We copy and pasted everything. Yeah, copy and paste is always the solution.
Are you sure? Are you confident? Let's see.
Well,
let's
run
see. This.
If it's not working, we'll fix it.
By the way, this might be very slow.
Well,
actually, no, 2 seconds.
Run it again, because 2 seconds I think is with compiling. Or... No, it's just... No, it's 2 seconds and a half of test. But well, still not terrible for us for being...
This is good.
Okay. Yeah, I'm curious to implement the matrix way. Curious from the memory point of view, a performance point of view. Probably we can do something next time with the other solution. Now, this is horrible because we copy and pasted like crazy.
Exactly. Yeah, every function and every type is duplicated. Now, my idea will be to use const generics, where we can use essentially an array that has a size that is defined by the generic constant. So something that will look, I'm going to duplicate again, but this is going to be the generic version.
Okay.
So then we should be able to remove 3D and 4D. So I think I'm going to do a struct because I think it's better. And then in a struct, we can just do point. In point, we can have const D, which is a usize. And this point is going to be essentially a wrapper type for I32 of size D. So basically what we are saying is that this type has a length that is going to become constant as soon as we specify this generic constant. So you can create points that are size 1, size 2, size 3, size 4, whatever you want. And the way you do that is something like this. You can say let p equal point, and then you can specify an array like 0, 1, 2, 3, 4. And Rust should be able, doesn't like t.
Open and close the brackets. Yeah.
And Rust should be able to understand that this is a point
of size 4.
Size 4. Alternatively, if there is an ambiguous case, I think you can do something like this here. That should work.
Okay.
And that should be the same. If you say 3, for instance, Rust should complain. You say 3. And
yeah, the 2D in your declaration in line 9 are not matching.
So, similarly,
Rust Analyzer is showing it to you like type point. It's not telling you what the D is, right?
Let me revert. Here is only telling me point. Yeah, it's not telling me that D actually. Let's make it 4.
Yeah, but it's not telling you, look, this is a point in 4 dimensions. You have to somehow, remember. But well, he's remembering it because
it will tell you if you are using it in a mismatching way.
Yeah, okay.
Okay, so then what we can do is to do the same for universe. So we do struct universe const D usize, and universe is going to wrap an hash set of a point of type D. So you can also combine essentially these types. So we are saying that hash set is always an hash set, but the contained type is of point generic D. So when you instantiate a universe, you are essentially locking in the dimension of your points. Make sense?
Okay.
So here we can say let U equal universe new. And this is not going to be enough for us because it doesn't know how many dimensions. So one way will be here to do universe of point 3, for instance. I think that should work. Should
No, it's not happy.
it? Let's see. Let's see why. Type provided when a constant was expected. Should we say?
No,
this?
universe of free. Universe of free, not universe of
Oh, right.
three.
We just need to say universe of 3. Yeah, you are correct.
Well, yeah. No, completely.
Then why doesn't like new?
Because you are not defining
because
a type.
we need an hash set new, I think. No?
But you're not defining type, you're defining struct. Is it different somehow? I mean, in line 7, we are using the type.
We need to do universe of hash set. We can do a constructor if we want to.
But well, it's just hash set of...
I think this will work.
Okay.
Because this is a different type. It's not an alias. Like here we were defining an alias. This is instead a type that is wrapping that original type hash set.
Yes, so it's not an alias anymore. And you can't do an alias with a const d. You can't do an alias with a parameter, no.
You can do an alias with a parameter. I don't think so. We could try, but I don't think so.
So like writing type universe const d equal to hash set point.
Let's try. Type, I'm going to call it u const
because we are lazy.
U sides, and then this is equal to this.
To the hash set, yeah. I don't know, I'm asking because I don't know.
But you can do that. Interesting. No, so you can also alias. It's complained that we are not using it.
But yes, true. You can also alias it. Oh, no, I have no strong opinions on this.
Okay, no, I prefer honestly the struct because it allows us to implement functions as part of the type. For instance, we could implement neighbors as part of the point. Like from a point, you can get all the neighbors if we want to.
Okay. This was just a curiosity. So
you
can implement an alias with types
constant generics,
with generics, constant generics. But we are going on the road of the struct because we want to add methods to it. Cool.
Okay, so next step will be to start to make this function more generic. Yes. So again, we are going to replicate it again, and then eventually we'll get rid of all the duplication. So let's remove point 3D, and let's just call it point. Here in the functions, you can also have generic. So we can say const d usides, and this point is going to now be depending on d, and this is going to be depending on d as well. And this sides, okay, now I don't know if this is going to work. Maybe we'll need a vector. Maybe. We'll see, because we could do what? 3 power of d, I guess, minus 1.
I don't know if you can be so...
I don't think we will do that.
Let's see. Superpower. Do 3 underline E32 or U sides. I don't know what. No.
Expected U sides. All of that needs to be a U sides.
Well, at this point, do 3 underline U sides. No, you don't have POV on U sides.
This is D.
May not be.
Yeah, cannot be used in const operations.
We tried. Can't you do like a ternary if d is 3? Well, okay, we have 3 dimensions and 4. We know that, but no, okay, nothing.
I think the easiest approach. Okay, Tommaso is suggesting to create an iterator, which might be interesting to do. I think I want to do a shortcut for now where we use a vector, just because it feels easier. And then
also a vector is, you can memorize a vector because we're going to call these over and over and over with the same parameters, and we are computing stuff more than once with an iterator because we are always redoing the same stuff. Instead, if it's a vector, we can memorize it with some kind of hash map. Yeah, but well, I don't know what is the simplest stuff to do at the moment.
Okay, what I will do is literally just a vec of
point
d.
Okay, let's go for the simple route.
for now. Now here we start with interesting math, because let mute points is gonna be a vec of
well, you can declare a vector.
Point. Actually, I think it's gonna figure out if we just do vec new, which we can just do like this. When we do the first insert, it should figure out exactly what is the type. Let's see if that's the case.
Okay.
So now points, this is what we are replacing. So we can remove that one. Okay, now it's interesting because we'll need to find a different approach here, right? We don't know how many for loops do we need to do. So one way would be to kind of linearize this for loop using that power expression, maybe.
Yes. And if we land on all zeros, we have to not add to the vector.
So it will be from I from 0 to 3 to the power of d
minus 1. Ah, no, but well, up to is already minus 1.
Yeah.
Or you can start, okay, let's say if it is 27, 0.27 will do 27 from 0 to 26. Cool. Okay.
Why doesn't like this?
I think it's you have to put it between brackets.
Okay, d as I32. U32. Fair enough.
Okay.
Because the exponent needs to be positive, I guess.
Yes, positive.
Okay, so now we have essentially a linearized version of this array, these nested loops, but we'll need to figure out from I how to calculate X, Y, Z, W, and whatever, right?
Yes.
So I suppose one thing we could do is let mute point. This is the current point, and initially we could do 0 and d.
Okay, we can do this now here. Okay, cool.
So this is just an array of d cells.
Can we do a loop d times?
D times, like Ruby, right?
D is a number. Cool. If the dimension is 3, I want to loop 3 times.
Yeah, what we could do is another for, like for whatever j in 0 d, something like that, right?
I don't think we need the number itself. We can just
yeah, you can use an underscore.
Yes.
But if you have the j, you know what, the specific position in the points here, right? Which position here we need to check.
True. We need.
So which, if it's X, Y, Z, or W, or whatever other imaginary dimension.
Can we modify I here? Can we modify it?
Inside the loop, you mean? Yeah. Like make it mutable?
Yes, basically we want to take I modulo 3 minus 1 and then divide I by 3.
Yes, but I think the easiest thing is to do n, let's say.
Yeah, mutable n.
I. Let mutable n, yes.
Okay.
And then what we want to do is
point of j equal I modulo 3 minus 1. But
point of j, yes, it's equal of
n, because we call it n.
Divided 3.
No, modulo 3, because it's the
modulo
number.
3, and then we reassign n.
Yeah, but minus 1, because we go minus 1, 0, 1, not 0, 1, 2.
You're right. And then we do
n integer division,
which I think is like this, of 3.
Yeah, exactly.
Right?
But okay, at this point, yes, between line 22 and 23, we have to say if not all the elements are 0, add to the vector. If the point is all zero, we don't have to add to the vector.
Yes, which is the same conditions we had here.
Yeah, but with multiple number of points in.
So if point is different from 0D, right?
Ah, cool. You can do that.
I think we can do that. Let's see. I have no idea. I'm guessing I likes it. And then what we do is points dot push. Is it? Yeah.
Push. Okay. Never remember.
And then we can pass a reference of. Actually, no. We just pass point. And then
yes,
at
because
the end of all
we are getting the point here. If you pass a reference, then we go in the lifetime land.
Is this good enough? Why doesn't like it? Oh yeah, we need to wrap this one. We need to say that this is a point of this, basically.
Yeah.
Is it gonna work? Yeah. I'm gonna call this point something like coordinates, I guess.
Point array, point coordinates.
Yeah. Okay, so that should be our generic equivalent of these neighbors 3D and neighbors 4D. Now we'll need to write this other one as a generic, count active neighbors, right?
Is possible to use that generic function that we did in one of our previous functions?
I guess yes and no, because we'll need to change all the types as well. And we'll need to change them everywhere, right?
Okay, no, it's too okay.
So it's probably easier to just keep going and we'll test it at the end.
Yes, sorry, it was just a question if we were able to test it mid path. Yeah, we can always add a test, but let's not do that. It's time consuming and we don't have a lot of time.
Yeah, I suppose if it doesn't work, we'll start to add tests for all these functions. For now, let's trust our skills. So there is another question here. Is the compiler complaining if for j goes to a d+1, for example, or it's gonna panic? Good question. If I understand the question is here, when we do coordinates j of something where this j could be bigger than d, right? Is the compiler gonna complain? And here we have squiggles. Consider using an iterator.
To loop over numbers? Guys, as numbers. Try to write go to 0 ... d+1 between round brackets to see if the compiler is complaining.
Say again, to go?
Line 19.
Put d+1, yeah.
Yeah, but between round brackets, I think, because...
we can even just do equal here, I think, which should be the same. No, it's not complaining.
It's not detecting that it's going overboard, no, it doesn't care.
Overflowing
it's overflowing the array that we create in line 17.
Also, it's giving us a bunch of squiggly lines. We are never using this index. Is it true? Yes. Why did I?
Yeah, because it comes from the previous solution.
Yeah, good. Fair enough. Okay, this one I have no idea what it wants. Use an iterator. Consider using an iterator chords.itermut.takeD.
Also, Luciano.
Okay, that's interesting. Look at this.
Sorry for the question. We are taking a parameter point. Do we use it?
Parameter point. All right, we forgot to do something. We forgot to sum the values. We lost something in translation. Here we were doing the sum. Yeah. Okay, good catch.
Yeah, but we have to do that after we add. We have to do that in line 24 because we still need it to be consistent.
Okay, so there are a bunch of interesting solutions here. So we need to do this for sure because this is plain wrong. But also, Tomasi suggested we could do chords.iter.enumerate and then do a map, which I think it's fair enough. So here basically will be chords.iter.enumerate.map. right? And now we have every single point. We have the j and the value of the point coordinate, I think.
And what we do with that?
With that, yeah, we create a new point, I suppose.
Yeah, but I don't know if we have to do that here, Luciano, because when in line 26 we compare all the coordinates to be 0, we are computing a delta, basic. Those are our cores are a delta.
Yeah, fair enough.
And we have to do that inside the if that is in line 26.
Okay, I'm going to try something else. I'm going to try to follow this suggestion here, which, if I understand correctly...
Needless range loop.
If I understand correctly, is telling us that we could do an iter mute. And then with an iter mute, what do you do?
We can iterate over coordinates, mutating it. Yeah, but we also need the j.
We'll need the enumerate, right?
We need j, because otherwise we don't know. No, we don't need j. We can just attack. No, you're right. We don't need j at that point, because we just take n. We have to do two stuff. Retarding n, but we also have to change n. So I don't know if you can.
Okay, so if you just map here, do you have a mutable reference of n? Yes, so we can just do this, I think. Here we can just do, rather than doing chords j, what we do is asterisk n equal this, plus we'll need to get the other one. So we still need to enumerate.
I'm losing you.
Wait, I'm getting there.
Yeah, do your stuff, but I remember that I lost you.
Okay, now we have I and n, where I is the current index. I'm going to call it j because otherwise it's confusing. J is the current index, so the current coordinate we're trying to sum, right?
But that n is not masking the n in line 17.
That n, yes.
N is our mutable copy of I.
But I don't think we'll need it anymore. That's what I'm saying, if we do this.
And we don't use I, so we don't know where we are.
But we have j.
Yeah, but we have to iterate I times, not j times.
So I times for every point. Then every single point, we do j times, where j is the current number from 0 to the dimension.
The first one is -1, -1, -1, for example, when I is 0. When I is 1, why this loop change to -1, -1, 0 if we don't use I?
I'm not following.
Okay. Do your stuff. Let's see if it works, but I'm lost.
So what I wanted to do is we want to apply this point to the neighbor. So the neighbor is just a relative position.
Yeah, but we were, like we did before, we could have applied it between line 27 and 28 and add it to the...
Okay, what I want to do is just do plus point, and then
yeah, but
point,
then
what does it have? 0, and we get j, I think. Right?
Yeah.
Would that work? And then we do... Oh, yeah, we still need n, do we? Yeah, I think I am mixing up two different things. Now I understand your point.
I can't follow you. It's probably... Yeah, I think you're mixing up stuff.
I was also mixing up two things.
Also because we have to check that the point that we are adding is not the point that is passed to us.
Yes.
So go back.
So let's go back to sanity, which was this one. So the only thing we need to do is this, where coordinates you want to add point, basically. Now we cannot do that yet. unless we implement the overload. But this is the idea, right?
Yes. And
Okay.
to do that, we can use the suggestion from before, that is coordinate map.
I'm going to call this relative coordinates because now it should make more sense.
Yeah. There we can add something like point.map with the, or relative coordinates.map is the same.
So we do like let chords equal relative chords dot enumerate, no, either.
Yeah, dot numerate, because yes,
enumerate.
Dot,
now
dot map. Now you will have two parameters here.
And here we will have I and...
But don't call it I because we already have I. Call it J.
Yeah, call it J and what? V for value. And basically what we need to do is to say
V plus point of J.
0.0 because it's the nested element.
We have to, okay, we have to unpack.
Yeah, this is a little bit ugly, but whatever. And now what do we do? Collect, I guess. Is it gonna work? We'll need to say that this is type I32D. Okay, why doesn't like it first? Oh, it needs to be like this.
Okay.
Okay, and then collect, why it doesn't like it? Cannot be built from an iterator. Okay, so you cannot collect stuff like that.
You can't collect an array. Okay.
Then, okay, that's not a big deal, I suppose, because we can do coordinates as
vector of integers. No.
Let's do mute coordinates. Again, we'll do the same crap. So 0 and D. And then we do chords either mute.
Okay.
Can we do either mute?
Yes, we want to mutate.
Yeah, and then enumerate. Now, this is what I wanted to do before.
Now it will be relative coordinates of J plus 0.0 of J in that map.
Now here, V is already the value. So what we can say is...
The values will always be 0. You initialized it to 0 in line 24.
Okay, so will be relative chords of
J.
Yeah. Plus this.
At this point, we don't use V. So
now this map, I don't think it's going to work because it's lazy. So we'll probably need a for each.
I lost you again. I lost you again.
Because map is not doing anything until you collect. And we don't want to collect. We just want to apply this function basically for every element there.
But do a for J in 0 to D and...
which is the same stuff that complains here, right?
Yeah, exactly. And this intermute was a try to solve it like before, but let's go for the simple way. Then we can refactor.
Yeah, let's do for
J. For J,
let's copy that. Yeah,
in 0D.
0D. And then
our
we do
chords of J is equal to relative chords of J plus point of 0 of J. Yeah, that guy there. Then obviously we can do that with a chaining of functions. We are not smart enough.
By the way, I created this. Is a little bit more readable.
Point of course now in line 29.
Line 29. Yes, chords. Good point. Good
okay,
point.
Probably out of this we have All the neighbor coordinates, probably.
By the way, notice how it's not complaining here and it's complaining here. Why?
I don't know why there is complaining and not there. I truly don't know, because it's exactly the same, except that we're doing a different stuff inside. Is exactly the same behavior, but probably because we are touching only relative chords in the previous loop. Instead, in the second one, we are touching 3 different stuff, and so the compiler is not understanding what we are doing.
Could be. Or maybe the compiler is thinking, if you really want to do it this way, I'm not going to bother you.
Okay, do what you want.
Okay, let's continue generalizing this stuff. So now this should be correct, hopefully.
Okay.
Then the next one we were trying to do was count active neighbors, right?
Yeah. Luckily, those 2 functions are not very different except from the types. I mean, they do exactly
now, yeah, we'll need to always do this const d usides, because now every function is generic. Point will be a point
d,
and universe will be a universe d.
And the rename from cube to universe is still called cube.
Oh, you're right. Let's rename there. Okay, is it
88 universe.0, because now it's wrapping
88? Well, first here we need to use neighbors of point, right? And this is giving us a vector. We iterate over the vector, we filter, and now we do universe.0, yes,
because
contains p. Why doesn't like it? Oh, of course, because we need to say, yeah, that's interesting. I didn't mention that. That basically this point here needs to be derive hash. But I think also you need equal and partial equal if you do that.
Okay.
And since we are at it, we are also going to throw at the debug in case we want to print something.
Okay, because with the line 6 and 3, it was able to derive the hash function because they are just a tuple of it's just an alias. This time to be able to hash that is not an alias anymore, is a struct, so it must be, it's not hashable by default. Okay.
Why is it complaining here? The trait hash is not implemented for hash set. Okay, universe doesn't need to be hashable. It's just the point that needs that.
No, yes, just the point.
Okay, now it's happy.
No, it's not that function. Okay,
this one.
So point of the universe of the give back a usize, iterate, contains, count. Okay, this was easy.
Now the last one is next state.
Is next
generic. State. Okay, so this is going to be fun. And after that, we should be able to start using our generic function.
To try to create a test. Part 1, generic version.
Okay, so this is again const d usides. Now all the universe is going to be a universe of type D, and it's going to return a new universe of type D. Now points to check is a hash set of point D, right? And now all the universe dot 0 dot iter, right?
Yes, because the universe itself is not iterable.
And then we do neighbors of point. I wonder if it's going to figure it out if we just do this. It does, so you don't need to specify D here.
Okay.
Because it sees D from point.
Yeah, BD come from line.
Okay, now points to check. Here we use the generic version. And that's up here is 0.
0 contains, because we are wrapping it basically.
And now why we cannot collect? I think because what?
No, let's read. Okay, a value type unit D cannot build from iterator over element type points.
We have no idea of this one.
We have to map it probably to contain it.
Why?
Okay, points to check is a Nash set of point.
Oh, we need to wrap it.
The universe,
because now it's a wrapper.
Yeah, it's a wrapper.
Okay, so
there
let's
you have to write
say
the universe of D of round or curly brackets. Oh my god.
something like this, basically.
Yeah, with round brackets. Okay. Yeah, because we have to wrap it because we are not aliasing but encapsulating.
Now here, what's the problem? Point. Oh, here is trying to move the point.
Because now we are not we are encapsulating, so we are encapsulating the points to check that is a Nash set. We are not returning it, but we are putting it inside universe, so we are creating universe and returning it. But that hash set is created in the function, so if we return universe with this hash set inside that is created inside the functions, how do we keep a reference to it?
We clone, honestly.
We clone like crazy.
For now, let's clone. Then we'll figure out if there is a better solution.
Is that one to clone or is the universe to clone? Okay.
I think it's the point we need to clone, right?
I was the one asking.
Now, here is the same, I guess. Now, I'm not going to say that this is cool. This is a shortcut.
Okay, let's try to, if he's just complaining about the fact that we don't use next state, let's try to do part one with this. Part one because it's smaller, just because of that.
Okay, so now what do we do? Basically, we say that universe, let me rename this guy.
And to write a new part one, don't change this one.
Okay, so we keep it as a reference.
Yes, part one generic. Gen.
Okay, so now universe rename.
Yeah. Type is universe new. Well, we didn't
Type is gonna be
universe hash set.
Okay, here we will have the same problem that we'll need to do the wrapping. So let's say data, right?
Yes, those are.
And this data is gonna be an hash set of
hash set
of let's do this of point B, right?
But we know that it's free here because part one is 3 dimensions.
And this is gonna be 3, yes. Okay. Now what we do is data insert, and now our universe is let universe equal universe of data. Is that gonna be enough? Yes, but why doesn't like new point? Because of course here the point we need to create it as a point. So this is gonna be
yeah, because we are wrapping again. I forgot.
This, I guess.
And it will infer that is free because the array. Okay.
Okay, and then the next state 3D needs to just become next state of universe. And now instead of being universe len, it's universe 0.len.
He's complaining that universe is not mutable.
Of course, fair enough. Needs to be mutable. Okay, is it gonna work?
Write a test, copy and paste the test for part one and create part one gen. That is not generator, it's generic. And use part one gen.
Fingers crossed. Let's see. Moment of truth.
Will it work?
Works. Nice.
Yeah. Can we go in the benchmarks?
In the benchmarks. Where do we have benches?
There.
Okay.
Import part one gen also in line 2.
Part and then okay.
Yeah. Clone line, copy, duplicate line 6.
And we do part 1 gen, and we call part 1 gen. Okay. How do we run this?
From the terminal, cargo, we have to go in the folder and run cargo bench.
Okay. How did you show the terminal?
Command shift back quote, control back quote. Is a Mac. I don't know a Mac.
No, that's terminal. New terminal. That was easier.
Okay.
So cargo bench.
Sorry. Try control back quote now. But you run it in the root.
Oh, right. Okay, I'm gonna
go in the folder. Otherwise, he's running all the benchmark, all the projects.
this guy cargo bench.
Yeah. Just for curiosity, control back quote is up opening and closing the terminal.
Control or command back quote?
Control. Try control.
Control, yes.
Okay.
Nice. So. Good to know.
Yeah, but because Mac, sometimes the control is replaced by the command, sometimes it's not. I don't know why they do this. I care about part 1 and part 1 gen. We run also part 2, but okay. So part 1 takes 3.7 milliseconds. The generalized version, let's see, is not exactly a correct way of running them. Because the machine, the machine is under the same load, but
slightly slower. I mean, not slightly; it's almost double.
That can be because the generalized version is not memoizing. I don't know.
But we never memoized also before, right?
Yeah, I think so. So it's slower. Probably is how we created the delta of the point, because free loops
also we are
doing one inside the other.
Also, we are cloning, which we were not doing before.
That we were not doing before, exactly. I don't know if with lifespan we can get rid of it. And also, before we were doing 4 loops, one inside the other. Now here we are doing the math. I don't know if doing the math is more expensive.
Tommaso is mentioned divisions are expensive.
But we can't do bit shift because 3 is not a power of 2. So we can't do bit shift of 2 bits because it's dividing by 4, bit shifting of 2. 3 is a... Also, we are bit shifting by d, so by the logarithm base 2 of d. So, probably there is some smart way of doing this. We can try to improve it probably next time. And you do time. I don't know if you have time.
What I want to do for today is to... I don't know. How do we clean up, though? Do we just leave the generalized version?
Do also part 2 gen.
And we see the difference?
We create the benchmark for part 2 gen, and then if the tests are all green, we commit like this, and then we clean up.
Okay, sounds good. So we do part 2 gen, and next time we'll try to
probably
clean up.
It's better if you copy and paste part 1 gen instead of copying and pasting part 2.
Good point, because we just need to change probably that 3 into 4, and that's it.
Yeah, and the creation in line that now is 178 and will become some other number.
This will be part 2 gen.
That point in line.
Is this the only thing that changes?
Line
this one will be 0.
Yeah, that one will be 0. I think is everything we have to change. So the code is very reusable this way. Probably also the parsing. Can we make that parsing?
We could probably generalize it. Yeah,
generalize the parsing with D that is adding enough zeros to go up to D, but we can create part.
So let's do this.
That one.
And this will be part 2 gen. Is it still working? A little bit slower.
Yeah, it's a little bit slower.
Which is expected. It's about 30% slower.
Yeah, but like Tommaso was saying, division costs a lot. We can figure out something smarter, but...
So this will be part 2 gen, and part 2 gen. And now that I know the control backtick, are we in the right folder? Yes, cargo bench.
Okay. We already saw that it's lower, but it's just to have the idea. Yes, probably we have to make it faster somehow. Yeah, he's telling us that now is a little bit slower, but it's because your machine is not always at the same load. Also, you are streaming, so. At 0.
Part 1 gen, well, it's less than 1%.
Yeah, but if the delta with cargo bench change by 0 something, basically is the same. And this one is new. It doesn't have a previous point of reference. Let's take it easy.
But this one is taking what?
Yeah. It's going from, if you scroll a little bit up, the part 2 is taking 131, this one 151.
It's not a huge difference. I was expecting more.
No, it is not a huge. But okay, we are not using memoids. We are not using a lot of stuff that we could use.
So when you say memoids, it's basically the idea that here, where we calculate all the neighbors, we are doing this for every single point every time.
In six iterations, we are asking the neighbors what are the neighbors of a point, probably 6 times or more.
Yeah, we are rebuilding this vector every single time, basically.
Exactly. This over and over and over. And before it was, in the other solution is an array, so even the allocation of a vector is more expensive. So if we can have some kind of hash map that say, look, I compute the neighbor of this point once, take it. And when you ask them again, I give you back from the hash map. I'm not giving it you back from the computing them. We can relative cores can be cached also because it's always the same. It's always -1, -1, -1 up to 1, 1, 1, excluding 0, 0, 0. So even the compute of relative cores can be cached in memory. So basically you compute it only once for every exercise. And then the relative the real coordinates, applying the relative coordinates, also you can cache also that one. So there is a lot of memoids that we can apply around. Probably not now. About that ether mute in line 21, we can dig in it.
But I will leave it for next time.
There are a lot of optimizations here. The point of this exercise of generalization is to show that you can write code that works on types that you don't know up front. So I have an array of 4, 5, 6, and the day works. Normally, to do this in Go, you have to do templating and code generation, for example.
Exactly. Also, one thing is that also the extra cost that we have is not, I mean, there is a whole theory in Rust that every abstraction should be 0 cost, right? Assuming that that's true, I think the only cost we are paying here is this vector, which is allocated on the heap, and the clone. So if we can remove both.
And the divisions, that's probably a photo.
And the divisions, yeah.
But also, if you cache the relative cores somehow in a lazy static, for example, you do the division only once. So you can keep them, but you can become way faster.
Yeah, the thing with lazy static, I tried once to use lazy static with const generic, and I couldn't figure out how to make it work. There might be a way, so it's interesting. If anyone knows, please send a PR or send us some reference that we can check.
Let's do a memoirs. You have an hash set, an hash map with 3 that points to the relative for 3, 4 that point to the relative of 4. If you want 5 and you don't have it, it's computing, putting in the hash map and giving it back to you. So the usual cache strategy for
I suppose that even these neighbors can receive the cache straight away. Like you can pass it And so you create it once from another function, and then you always pass. So we split this in two. That could be an easy way to do a memoize. It's not really a memoize. It's more pre-compute something, then I'm going to reuse that something over and over.
Yes.
But I mean, I'll leave it either for next time or for a PR that maybe
somebody
we'll do
can
offline.
drop. Cool.
Okay, so I'm going to commit all this stuff and we'll do the closing.
So let's wrap it up. You can find the recording on YouTube. The link is on the Twitch in the About session. If you're watching this on YouTube, we do streaming on Twitch every Monday at 5 p.m. UTC. Make sure to check the Twitch link in the YouTube description and vice versa. So follow us so you can be notified when we upload the new content. Feel free to leave us comments, open PR, tell us that we are a bunch of idiots and stuff like that. We are here to learn. The repository is in the banner that you can see on the bottom. Everything is well accepted. We are trying to learn Rust. We are not doing beautiful solution, like you can see, but we are seeing interesting concept and we try to run it, to learn it comparing to other languages that we know. Our Rust is not the most idiomatic one. For that, you have to wait for a pull request from Tommaso. If you know a better way of doing stuff, open a pull request, send us a message. We are on Twitter, LinkedIn, Twitch. We are everywhere. Don't worry. Thank you for all the suggestions in the comments. Thank you to all the people in the chat. Do we want to raid somebody?
That's what I'm doing. I'm searching for somebody to raid. Let's see. Is it in English? No, this is in Portuguese. So I'm not going to raid that. Sorry.
Well, you can learn a new language and a new language. A new programming language and a new human language at the same time. No?
Nobody is streaming at this time. Maybe. Let's see.
Is not bank holiday in
okay,
the USA
I found
today?
Somebody. Maybe that's why. Okay, you can learn how to do video games. See you next time.
Thank you. See you. Bye.